everyone, Mrs. V here, and today is part 3 of our series on pH of weak acids and their Ka values. Today we're going to look at how you calculate the Ka value when you're given the pH and the concentration of the acid. No time to lose. Whiteboard on, let's go. This is the third type of question that you're likely to get when we're dealing with the pH of weak acids and their Ka values. And that's that you need to find Ka when you're given the pH and given the concentration. In this example, I'm going to work with a general acid, HA. Okay, so here we have our weak acid, HA, and we're going to be working with that. Now, what that means is, as long as you understand that HA can be any acid and that A- is its conjugate base, you can apply this particular working out to any of your acids. So this is any acid and this is the conjugate base. So if we were looking at HCl, the conjugate base there would be Cl-. If you're looking at nitric acid, then the conjugate base would be NO3-. If you were looking at acetic acid, then A- would be CH3COO-. Last video we did benzoic acid. The conjugate base of that would be the benzoate ion. So when we're doing our working for this, it does not matter one little bit what your acid actually is. The same steps are used. Let's have a look at the ionization equation for HA. So ionization in water, in equilibrium with A-, the conjugate base, and the hydronium ion. And what are we asked to find out? We're asked to find out Ka. So let's write an expression for Ka. So Ka is concentration of A-, concentration of H3O+, over concentration of HA. Remember, water's not included, it's a pure liquid. What are we told? We are told the concentration of HA. So we know this. We are told the pH. We have a look at the pH. 4.6. We can work out the concentration of H3O+ from the pH. So pH is equal to 4.6. And we know that concentration of H3O+ can be worked out by 10 to the minus pH. So that's equal to 10 to the minus 4.6, which is 2.5 times by 10 to the minus 5 moles per litre. So check, we have concentration of H3O+. But what about the concentration of A-? Well, if we go back to our original equation, we can see that in this ionization equation, there is a 1-to-1 mole ratio between A- and H3O+. And therefore, when HA ionizes, we're going to get the same number of A- as H3O+. So that means that the concentration of A- will be exactly the same as the concentration of H3O+. Check, we have A-. Now I can hear you all making the query. I can hear you going, but Mrs. V, surely the equilibrium concentration of HA is different to the original concentration of HA. And you'd be quite right. because in this ionization, if we did an ice table, HA would start at 0.32 moles per litre, and our A minus and H3O plus would start at 0. So if we were doing an ice table, then if our equilibrium concentration of H3O plus was 2.5 times by 10 to the minus 5, and A minus is also 2.5 times 10 to the minus 5, then we would expect, given that that is therefore a change of plus 2.5 times 10 to the minus 5, that's also, we would expect to have to take away 2.5 times by 10 to the minus 5 here. So our equilibrium concentration would be 0.32 minus 2.5 times by 10 to the minus 5. And that's very true. However, when you have a look at it, 0.32, if you subtract 2.5 times 10 to the minus 5, this thing is so tiny that subtracting it is not going to change 0.32 at all. That is, when we're working here, we're working with two significant figures. So any change is going to occur way outside that range. So we can assume that concentration of HA is actually just 0.32 moles per litre. Now we know everything. It's just a matter of plug and chug. So our Ka value is equal to concentration of A minus concentration of H3O plus. Well, they're both 2.5 times by 10 to the minus 5. So we'll just square that, divided by 0.32. Run that through your calculator, and you get 2.0 times 10 to the minus 9. And there it is. Ka is 2.0 times 10 to the minus 9. We've got to the end. We've managed to solve it. And that's a wrap for today. I will see you in our next video.